And now for section 4.2, the mean value theorem. The word mean right here in math means average, so it could also be called the average value theorem. By way of an example, suppose that you're driving 50 miles an hour. And then you look around, notice that there are no highway patrol around, so you speed up to 70 miles per hour. So then the question is, was there ever a time when you went from here to here, was there ever a time when you were going 60 miles an hour? So the answer is yes, because in real life, velocity is continuous, which means there's no holes or gaps. If you're going to go from 50 to 70, then you need to go to 51, 52, etc. So there must be a time when you were going 60. And what's the average of 50 and 70? You got it, 60. So the average value theorem. Now it actually goes like this. It's often abbreviated as the MVT, and you know that a theorem is important when it can go by its initials, MVT. So suppose that you've got a continuous function, and I'll call it f of x. And it's going to be continuous on the interval from a to b. Now before I finish the theorem, let me just draw a nice pretty picture. So here's the x and y axis. It's going to go from a to b. First of all, substitute a in the function, and then that's going to be a height of f of a. And then the function meanders along, and eventually it gets over to here. And let's say that's a height of f of b. So then get a nice little straight edge and connect the two dots. Right now I'm just ignoring what's in between. Connect the two dots. And that, you may remember, is called a secant line. And if you find the slope of the secant line, it's basically saying the function went from this height right here, so f of a, up to this height, and it took this long to do it. So when you find that slope, that's the average rate that it was going up to get from this point to this point. Now, take that same straight edge, line it up with the secant line, and then, keeping it at the exact same angle, move it, move it, move it until it's touching the function at just one point. Then make what we call the tangent line. And because I kept it at the same angle, these two are parallel. So that's going to happen at this point right here, and then that point on the x-axis is called C. So the continuation of this sentence goes, there is a number C, and it's between the A and the B, as you can see on my picture. So the number C is in the interval from A to B, and the final conclusion is the derivative at the point C, which is saying the slope of the tangent line, so this one's slope, the red one's slope, is equal to the secant line slope. And for that, you subtract the two y values, and then subtract the two x values. When you divide them, that's rise over run, so that's slope. So it's saying the slope of the tangent line equals the slope of the secant line. All right. Makes a beautiful picture. It's a beautiful theorem. And then how could we actually use it? Well, for example, number one. So now find the value c that is guaranteed by the mean value theorem. And the continuous function is going to be x cubed minus 2x squared plus x plus 1, and the interval is from 0 to 2. So the first thing that I'm going to do is this part. First, find the slope of the secant line. After that, I'll take the derivative and I'll set them equal to each other. So first, for the slope of the secant line. So the slope of the secant line is going to equal f of 2 minus f of 0 divided by 2 minus 0. Now f of 2. So this is going to be 2 cubed minus 2 times 2 squared plus 2 plus 1. So that takes care of this part. Then when you substitute in a 0, that's going to be 0 and 0 and 0 and 1. So then subtract that, minus 1. And then the whole thing is divided by 2 minus 0. And then this is going to be 4 times 2, that's going to be 8, so that's going to make it a negative 8. This is a positive 8, so those two actually cancel each other out. And these two cancel each other out, so all that's left on the top is a 2. On the bottom is a 2, so it equals 1. Now, let's do the derivative part. So now, take the derivative, which is going to be 3x squared minus, that's supposed to say 2 times 2x plus 1. And then substitute the value c, so that's going to be 3c squared minus 4 times c plus 1. And there has to be a place where that equals the slope of the secant line. And then solve for c. So you could subtract 1 from both sides, setting it equal to 0. And when you do, it's going to actually cancel this 1 right here, leaving just this. And then we could factor out c, and then it's going to leave 3c minus 4. So you set this one equal to 0, and set this one equal to 0. And then add 4 to both sides, and then divide by 3. And so we actually get 2 answers. C is a 0 and 1 1/3. Now, it has to be between these two numbers, and it cannot include either one of the numbers, because the theorem said, here it is, that you can't include the a or the b. So that means that this can't be included. So the final answer is 4/3 or 1 1/3. All right. Now on to example number 2, but first, a brief commercial. And the commercial is for Rolle's theorem. So Rolle basically had one specific case. So basically this is take the mean value theorem with the extra special case that f of b is equal to f of a. So here's the a, here's the b. And whatever this height is, this height has to be the same. So whatever that height is, f of b equals f of a. And then the function is continuous, it does whatever, looks something like this. Well, when you do the f of b minus f of a over b minus a, that part of the mean value theorem, since f of b and f of a are equal, that means it equals 0 over b minus a, or in other words, it equals 0. Which then means there must be a place right here, C, where the derivative is equal to 0. So f prime of c is equal to 0. So that's Rolle's theorem. It basically says there must be a place where the derivative equals 0, and that c has to be between the a and the b. So for example number 2, verify Rolle's theorem. So that means we need to verify this part and then verify this part. So the function is going to be sine of x over 2 on the interval from 0 to 2 pi. So first of all, we need to do this part. So this is going to be the 2 pi and this is going to be the 0. So f of 2 pi minus f of 0 over 2 pi minus 0. So to substitute this into the sine function, so the first one, when you substitute 2 pi in right there, the 2 on the top and 2 on the bottom are going to cancel. It's just going to leave sine of pi. And then sine of pi, that's equal to 0. Sine of 0 is also equal to 0. So it passes the first part, that's equal to 0. Now there has to be somewhere where the derivative equals 0. So take the derivative, and the derivative of sine is cosine. But then don't forget the chain rule. Take the derivative of the inside, which is going to be 1 over 2. Then I'm just going to change it to the letter c. So there's somewhere where cosine of c over 2 times a half is equal to 0. Well, I know the number 1/2 is not going to equal 0, so when does cosine equal 0? Well, the cosine graph looks like this. It starts at 1, it goes down to -1, and then it goes back up, and then here would be 2 pi. Which means right here, that's going to be pi, and where cosine equals 0, that's pi over 2. That means this part in here is equal to pi over 2. So that means that c over 2 is equal to pi over 2. Then multiply both sides by 2, and that means that c is equal to pi. Then it looks like I'm done. I just need to check, is this in that interval? And it sure is, which means we're done with that one. Then on to a very interesting use of the mean value theorem. So for example number 3, prove that sine of x equal to 2x minus 1 prove that that has only one solution. Not 2 solutions, not 12 solutions, but only one solution. And then I just want to show you on a calculator what it's talking about. So let me change this back to radians, and then graph sine x, also graph 2x minus 1. And then I'm just going to go to zoom standard. So there goes the sine function, up, down, up, down, up, down. and then the line 2x minus 1 is only going to cross it one time, just right there. But now prove it. Prove that this red line right here doesn't miraculously come back down and hit the sine function again. Prove that there's only one solution. So another way to rewrite this is you could subtract 2x and add 1, put everything on one side, and then it's set equal to 0. Next up, we're going to have that as our function. So let f of x equal sine of x minus 2x plus 1. And we want to show there's only one place where this equals 0. Now what we do is, it's saying that it only has one root, which we saw in the graphing calculator. Well, suppose that there's two answers. So suppose that f of x has two roots, or in other words, two values that make it equal to 0. And then I'm going to call them a and b. So when you plug in a, it's a solution, so it's going to equal 0. When you plug in b, it's a solution, so it's going to equal 0. So if you look at the xy axis, let's say here's the a, that's one solution, so it equals 0. That's b, that's another solution, so it equals 0. And then the function's continuous, so it's going to do something like this. And then by Rolle's theorem, that means that somewhere like right here, the derivative is equal to 0. So there's going to be some value c that's in between the a and the b where the derivative will equal 0. And then let's see if that's true. Take the derivative. So the derivative of sine is cosine. The derivative of negative 2x is negative 2, and the derivative of 1 is 0. And then call that the letter c, or the number c, and the derivative has to equal 0. Then add 2 to both sides, and then that says that cosine is equal to 2. And that is impossible. Impossible. Because the biggest that cosine gets is 1. So the cosine graph goes like this. So it always ranges between a positive 1 and a negative 1. It never goes up here to 2. So that means that this is impossible, which means this is impossible, this is impossible, and finally my supposition that there's two answers, that's impossible. So it cannot have multiple roots. Because if it can't have 2 of them, it can't have 3 of them, can't have 4 of them, it can't have more than just one. And now on to the last example, which is even a completely different way to use the mean value theorem / Rolle's theorem. So for example, number 4. One of my favorite subjects, long distance running. So there's these two runners, and they're going to run a marathon. And because it's a race, they start at the same time. And by coincidence, they finish in a tie, so they finish at the same time. Now, with this situation, there's a couple of possibilities. One is they're very good friends and they ran the whole race together side by side chatting and talking and having a good time. Or it could be that one of them is very competitive, took off really fast, but then at mile 18 ran out of gas and then just slowly finished the race. And the other person was consistent all the way through. Eventually, they caught up to that person right at the finish line and they tied. Either way, prove that there must be a moment when they ran the same pace. Or in other words, their derivatives were equal. Because derivative means how fast they're going, so we're trying to show that at some point their derivatives are equal. So let's say one person is Frank, and then this function is going to be the distance for Frank. So you can plug in 10 minutes or you can plug in 2 hours and it will tell you how far Frank is through the race. And then this is Helene. So at the beginning, at the start of the race, that would be time 0. So that means that f of, and whatever time they started the race, maybe it was 8 a.m. or maybe it was 6 a.m., whatever that time was, put it right here. And since that's the start of the race, Frank has not run yet. And Helene has run 0 miles. Then at the end of the race, Frank, so let's say that it took 3 hours, so that's going to be B. And then a marathon is 26.2 miles. And for Helene, the B is going to be exactly the same because they finished at the same time. And she completed the 26.2 miles. Almost done. Then let D be the distance between them. So that means that D is equal to, just subtract the 2 functions, and then that'll tell you the distance between them. So at the beginning of the race, whether that was 8 a.m. or 6 a.m., then they have run 0. And here's time B. And right now I'm going to graph the D function. So that's subtract these 2, the distance between them is 0. Then at time B, subtract these 2, and that's the distance between them, which means the distance between them is 0, which, like all the other ones, means there's a continuous function. And that means that there's going to be a point right here where the derivative equals 0. So this is going to be the number C. So there has to be at least one point. There could even be another point, but there has to be at least one point when the derivative equals 0. So now take the derivative. That means take the derivative of Frank, so that's how fast Frank is running. Take the derivative of Helene, and that's how fast Helene is running. And there has to be a place where the derivative equals 0. And that's going to happen at time C. And then simply take this one and add it to the other side. Oh, this is supposed to be the letter C. And so that means the derivative of H equals the derivative of F. And because derivative means how fast, that means that Helene's velocity equals Frank's velocity. So that means they were running at the same rate. All right, so that's section 4.2.